All right, so welcome to the video I was supposed to make a couple of days ago, but unfortunately I was sick, so I didn't get a chance to make it over the weekend. But here, let's kind of quickly go over all the stuff we learned from waves. So again, this portion here, so this is the equation for a periodic or harmonic or traveling wave. So this determines the displacement away from equilibrium for any position or any time. We have the first part, which is the angular frequency. So again, this has to do with harmonic oscillation related to the regular frequency this way. The K here is the wave number, not the spring constant. So this is related to the wavelength by 2 pi divided by the wavelength, where again, the wavelength is the distance between successive peaks. We have the velocity or the speed of the wave for a general wave, which is the wavelength times the frequency, or also the angular frequency divided by the wave number. And then we have specifically the wave on a string. So this is the square root of the tension divided by the linear mass density. And just to remind ourselves real quick, the plus sign here means that it is a left moving wave, while the right here, or the negative sign, I should say, is for the right moving wave. And then we had the standing waves. So we had the fixed, or also known as close. So in this case, we have n equals 1, which is called the fundamental. So this is the simplest we can have, which is half a wavelength. We have the n is equal to 2, which is a full wavelength. N is equal to 3, which is 1.5 or 3 halves wavelength. So follow that down. What we get then is that the wavelength for the nth harmonic. So again, we have the fundamental, which is n is equal to 1. This would be our second harmonic, and then our third harmonic, and etc. So that's the wavelength for each one, which is twice the length divided by the harmonic. And n here is going to go from 1 all the way out to infinity. And then we also have the given frequency associated with each one is the harmonic times the speed at which the wave is traveling, divided by twice the length of the, in this case, string. So this is the length of the string. And then these guys have to satisfy this. This is where this expression actually comes from, and the fact that the speed of the wave, which is fixed, is then equal to the wavelength of the harmonic times then the frequency. So good. So basically, all we want to do now is apply all this stuff now to a very specific wave, which is then our sound waves. So we talked about sound waves before. As we said was that we had some sort of like speaker here. So say, here's my speaker, which is then going to vibrate. So this guy is going to oscillate back and forth. And what that's going to do is it's going to create over and under densities. So what happens then is near the speaker, for example, we're going to get a high concentration of particles basically being squished together, right? So in this case, this is going to have a very high pressure. So if you think about it, what this means then is if you walk into a room, so here's say my room, and nothing is happening in that room. So let's say you first walk into the classroom, nobody's in there. So what that means then is that this thing is going to have some sort of pressure which is equal to a constant. So this pressure here, which is a high pressure, is actually a change in pressure, which is above this average pressure. So this is going to be bigger than the average pressure. Now, as the wave travels, you're going to get many of these spots here, which are then all high pressures. So these are what are known as compressions. Now, in between, now you're going to get particles which are basically spread out a lot more, which means that these are then going to have low pressure areas, which are what are known as rarefactions. So again, all this means is that the pressure in this area then, or the change in pressure, is then less than the average pressure. So what happens is, again, these particles, as we talked about in class, don't want to stay in high pressure. They want to move to a low pressure system. So these ones are going to spread out in this direction. These ones are going to spread out in this direction, which means that the locations of these rarefactions and compressions are going to switch. So basically, I'm going to then get a compression here. And then same thing over here. These ones want to move away. So this then becomes a compression. And then you get a rarefaction in between, and etc. And this is what causes the wave to actually propagate. Now, Let's think about it in terms of displacement. Okay, so in this case, we're talking about the change in pressure, but let's think about the displacement. So what's happening here is the particles which are in the middle of this compression or this high pressure are basically exactly at equilibrium position. So all these particles which are around it are initially compressed inward, which means all the ones that are in the center haven't moved at all, which means that even though we're at a high pressure, the displacement in this case, so our displacement D is equal to zero, right? Now, when it comes to the rare fractions, again, since all these particles are being pushed inward and these ones are being pushed in this direction, then that means they're going to have maximum displacement. So in our rare fractions here, in this case, our displacement in this case will be equal to a maximum, right? Even though the pressure will be low in this case. So ultimately, all this means then is we can define or describe a sound wave. Let me switch over to a picture here. In terms of either pressure or in terms of displacements, but they're 90 degrees out of phase with each other, right? Which basically means that what? If the pressure is zero, so it's at the average pressure, or the change of pressure, I should say, is at zero, then we're going to have maximum displacement. And then when the pressure is equal to a maximum, or the change in pressure is equal to a maximum, then in this case, we're going to correspond then to a zero displacement. And then again, it just keeps going that way. So ultimately, what that means then is each one of the two waves are described in exactly the same form, right? So they're still going to be in phase, or at least the wave number is still going to be the same. The angular frequency is going to be the same. The phase constant will be the same. But ultimately, what happens is that each one is shifted from each other by 90 degrees or pi over 2 radians, which means that one of them is going to be defined in terms of cosine. The other one then be defined in terms of a sine, because if I switch each one of them by, or if I switch one of them by pi over 2, that just brings it to the other one. Again, the amplitudes will be different because the displacement won't be the same as the change in pressure. But again, those two guys are going to be strictly related to each other. Now, it also turns out that the speed at which sound waves travel is actually dependent on the speed. So how fast this guy is moving, so the velocity of the speed of sound in air, as we saw in lab, is actually going to be dependent on many things, actually. So things like the temperature, barometric pressure, humidity, all these different things. But in terms of temperature, anyways, the speed of sound in air, which is temperature dependent, is equal to 331 meters per second times the square root of 1 plus the temperature in degrees Celsius divided by 273 to put it into Kelvin. So all you're doing here is you're transforming then the temperature in Celsius to in Kelvin, because again, we're working with SI units, and of course, SI units has to be in Kelvin. So this is the speed at which a sound wave is going to travel. So in a problem, typically we'll either give you the temperature, and then from there, you'll have to calculate the velocity, or we'll give you the velocity and you would have to calculate the temperature, or we'll just tell you this is the velocity at which it's moving just to make things a little bit easier. But again, ultimately, it's just going to be dependent on the temperature. Now, it turns out that a human being with good hearing, so unlike myself, can hear a wide range of frequencies. So it turns out that for a human with good hearing, the frequency that we hear is somewhere between about 20 hertz and about 20,000 hertz. So this is the frequency range at which a human can hear. Now, of course, I can't do this on the video. So tomorrow, when we come into class, I will bring in a tone generator and I'm going to test your guys' hearing just to see how everybody does. So if you listen to your music too loud, of course, then your frequency at which you hear will be less. It also depends on if you had a lot of ear infections as a kid, you'll kill, your inner ear, get some scar tissue, and then you won't be able to hear as well as a lot of people. So won't be able to pick up as many frequencies. But I'll test you guys. We'll see how you actually do. Contrast that when something with like a dog. Right, so a dog can hear from around 20 hertz, same as us, but they can actually hear much, much higher frequencies than we can. So they can actually hear to about 45,000 hertz. So this is why If you know anybody who has a dog whistle, or have you ever seen a dog whistle, when somebody blows the dog whistle, it doesn't bother you at all, but all the dogs in the neighborhood are just kind of freaking out. And the reason for that is that it's a much higher pitch than what it is that we can actually hear. So in this case, our body cannot interpret what it is that we actually hear. And the reason for that is because two different things. So when you're talking about low frequencies, it's your body actually acts as the receiver. So when you're talking about things like very low frequencies, like AM radio type stations, for example, they use very low frequencies where the wavelength is about the size of your car. So for most bass sounding things, like low bass, your resonance chamber is actually your body, primarily your chest. So you actually feel it vibrating in your body. But when it comes to higher frequencies, inside of our ear, we have little tiny hairs where the size of the hair is about the size of the wavelength. So as the wavelength decreases, i.e., gets smaller, the frequency gets higher because, again, the speed of sound in air is fixed. So, but the size of our hairs inside of our eardrums are only so small that for really, really high frequencies, our small hairs are not small enough to actually pick them up. So now let's talk about what's known as the how loud we hear sound. So let's talk about sound loudness. So our perception of sound loudness basically goes as roughly the logarithm in base 10 of the intensity. Mhm. So basically, the intensity of the wave is proportional to the amplitude squared, right? Where the amplitude squared is proportional to the energy. So the intensity of the wave has to do with the energy of the wave, which has to do with the amplitude squared. So the bigger the amplitude, the greater amount of energy it has, and then the greater the amount of the intensity. So what we hear as loudness, or how loud something is, has to do with the logarithm of this guy. So the way that we actually determine this is what's known as decibels. I know how to spell. There we go. Decibels. So for decibels, what it does is it basically relates the intensity at a given point to what's known as the threshold of hearing. So what's the threshold of hearing? So the threshold of hearing is the minimum amount of sound necessary for a human being of good hearing, again, to just perceive as something. So they can just start to hear it at the threshold of hearing. So the threshold of hearing, we're going to take as a constant. So threshold of hearing, I0 is given as 10 to the minus 12 watts per meter squared, because this is an intensity. So an intensity, if we look at our units, this thing then has units of energy per time, because that's a watt, divided then by a meter squared, which is the same thing then as what? In energy per time per meter squared, or in this case, per area. Okay. So this is the intensity, or again, we know a watt or energy per time is the same thing as power. So this is power divided by area. So this is what we call intensity. So let's put everything together. So what we call the loudness, or in this case, the decibels, we're going to call that guy beta. And then this guy is again, loudness. So this guy is beta is equal to 10 decibels times then the log of base 10 of then the intensity divided by the threshold of hearing. So again, it's a relationship between the intensity at a given point versus this minimum amount of intensity that we need to actually hear something. Now, the reason I say it's at a given point is because we all know by experience that the further I get away from some sort of source, so let's say I have some sort of source here, so this is my source, and then let's say this guy is generating sound waves, where these sound waves then move outward at then the speed of sound. So this is V air. Mhm. So as this guy moves outward, we know that if we're standing somewhere like here, very close to the sound source, then we're going to hear something very loud, right? So we're going to have a huge, or at least a large beta in this case. So this beta is going to be large. But then as I move further away from it, so I get somewhere out here, then the size of beta in this case is going to decrease. So this might be a, I don't know, a medium beta. And then if I get really far away, something like out here, then in this case, then beta is going to be very small. Right. So again, if some sort of event is going on at USI and I live on the east side, I'm not going to hear it because it's just too far away, right? So we know then is that what? The intensity has to decrease as we get further and further and further away from the actual source of the sound. So how does the intensity, in this case, depend on the position? So let's look at this guy. So in this case, we're going to look at what's known as a point source where our point source is, basically a dot. I'm going to draw that basically as a little speaker here. And we're going to assume that the source in this case is homogeneous, which means that it's the same everywhere. So this is the same everywhere. So that means in both directions. So if I drew like a sphere around this guy, at any point along the sphere, it would have exactly the same intensity. And it's also what's called isotropic, which means that it goes in all directions. Kind of the same thing in a way, but basically all that means is it's not favoring one direction or another direction, right? So again, all that means then again is if I look at some sort of fixed radius, we're then going to have the same intensity along this sphere, right? This is going to create some sort of sphere. Now, as again, the sound travels outward due to the fact that it's a wave moving outward, the size of the sphere gets bigger and bigger and bigger and bigger, right? So each one of these has their own radius, but again, each one of these spheres gets bigger and bigger and bigger and bigger. Now, what's happening though is that the source here is giving off an energy per unit time, which is the power. So that power that it's giving off is contained in each one of these different spheres that is moving outward. But what ends up being true is that the power in each one of these spheres is identically the same. So the amount of power given in the black sphere versus that of the green sphere versus the yellowish color sphere here are all the same because the energy per unit time carried by each one of the waves is exactly the same. It doesn't dissipate in this case. Of course, that's not 100% true. So what ends up happening is as it goes away, it does end up being partially absorbed into the air, which actually causes it to decrease less or actually decrease faster. But in this case, we're going to pretend that it's always the same. So the difference between if I was standing, say, here versus if I was standing here is the fraction of the sphere at which it is that I sampled, right? So if I'm looking at the size of me relative to the size of the black sphere, I'm a big proportion compared to the size of the sphere. But as the sphere goes outward and gets bigger and bigger and bigger and bigger, that means that the amount of fraction of the surface area of the sphere that I encounter here is much smaller than the amount of surface area I see here. So the intensity then, as we said on the previous page here, or 2 pages ago, is the power per unit area. So what that means then is what? So the power in all three of these are the same, but what's different is the surface area of each one of these spheres. So this is going to be the power per surface area that we encounter of each one of these spheres, which then is going to be the same thing as the power divided by 4 pi r squared, because the surface area of a sphere is simply 4 pi r squared, or the other way to think about it is that the surface area is equal to the derivative of the volume with respect to position. So this is the same thing then as the derivative with respect to position of then 4/3 pi r cubed. So when I take the derivative, this kills this, which then gives me the 4 pi r squared. So this then is the surface area, right? So this is then the intensity. So the intensity of the sound at any location relative to the source then falls off as 1 over r squared. So basically all this means is what if I plotted the intensity of the sound relative to my position away from the sphere, or in this case, the source, this thing then is going to decrease something like this. right? So this is going to go as a 1 over r squared. Let me draw that a little bit better. There we go. And then this thing is eventually going to go to 0 somewhere out here. So the farther I get away from it as sound or as my distance goes to infinity, the intensity is going to go to 0. But again, the intensity at some point as I move away is going to fall below this kind of threshold of hearing. So this will be my threshold of hearing, for example. So I'm not going to hear it anymore when it falls below that threshold of hearing. Cool. So let's put all these things together in a couple problems here and see how this goes. So the first part then says, or at least my first problem here, says what? So let's look at this one. So this says that the intensity of a sound wave from a jet airplane. So let's say here's my jet. Okay, so here's my jet. Something like this. Beautiful. So there's my jet. So the intensity at takeoff. So this guy is taking off. Right? Something like this. At 5 meters away. So if this is my distance, let's call that R5 equals to 5 meters away. So if I'm standing here, then the intensity at this part, let's call that I5, is the same thing as 1 times 10 to the 2 watts per meter squared. Right? Or if you want to think about it, this is 100 watts per meter squared. So what it wants me to find then is if I'm standing some other distance away, so let's say R120, which means that this is 120 meters away, what then is the intensity at this location? So let's call that I120. Okay, so what is I120? So what? So as we just said, what has to be true is that the power at this location has to be the same as the power at this location. So ultimately, all that means then is we can solve, say, the first one for the power. So let's do that. So in this case, we know that the intensity I5 then is equal to the power divided by the surface area, which is going to be 4 pi R5 squared. So let's solve that for the power. So this as my power then is going to be 4 pi R5 squared times the intensity at that point. Now, since that has to be the same power that is here, let's plug that now into the expression for I120. So I120 then is going to be the same thing as the power divided by the cross-sectional or the surface area, which is then 4 pi R120 squared. Now let's take this guy and put this in here to create a ratio. So this is going to be the same thing then as what? 4 pi R5 squared divided by 4 pi R120 squared, all times I5. So in this case, the 4 pi's are going to cancel. So at the end of the day, I'm going to get then I5 times the square of the ratio of R5 to R120. So at the end of the day, it's the same thing then as what? 100 watts per meter squared times then 5 divided by 120. Now in this case, of course, the meters are going to square or cancel out, so I'm not worried about that. So plugging my numbers, what I find in this case then is that the intensity at this point is 0.174 watts per meter squared. So this is my intensity at this point. So this is example number 1. Example number 2. So let's do another one. So example number 2 then says the source of a sound wave has a power of 1 microwatts. Okay, so let's say here is my source. Okay. And then this guy has a power which is 1 microwatts. Okay. And just so everybody knows, 1 is the same thing as 1 times 10 to the minus 6 watts. So this is micro. So it says if it is a point source. So the first thing it wants us to do then is part A, find the intensity, I3, when it is R3 equals to 3 meters away. Okay, so what is the intensity 3 meters away? So let's say I'm somewhere, I don't know, out here. So this is my R3. What is my intensity at this point? And then part B, we then want to know what is the sound level or what is the sound level in decibels. So how many decibels do we hear at this point? So let's call that beta 3 just for funsies. So let's do part A first. So part A, good. So again, we know now that what? The intensity I3 is simply then equal to the power divided by the surface area. So that's then going to be simply what? 4 over divided by 4 pi R3 squared. So let's put our numbers. So it's going to be 1 times 10 to the minus 6 watts divided then by 4 times pi times 3 meters squared. Right? Plug in my numbers. What I find in this case then is this is 8.84 times 10 to the minus 9 watts per meter squared. Now, for part B, we know the sound level intensity beta is the same thing as 10 decibels times the log base 10 of the intensity I3 divided by the threshold of hearing I0. So it's the same thing then as 10 decibels times the log base 10 of then, plug in our numbers, so 8.84 times 10 to the minus 9 divided by 10 to the minus 12. So this guy then works out to be 39.5 decibels. So this is my sound level intensity. Okay, not too bad. So now, since sound is a wave, this means that sound waves can also interfere. So let's look at the interference of sound waves. So these guys can actually interfere with each other. So let's say, for example, I have two sources. So here's source number one and then source number two. And let's say each one of these guys is giving out a wave. So here is my wave for the first one, and then here is my wave for the second one. Now, each one of these guys, of course, is going to propagate outward with some velocity, right? Which the velocity in this case is going to be the same. And let's assume in this case that each one has the same frequency and that these guys are going to be in phase with each other, which basically means that each one of them are going to give off a wave crest at the same time. So one of them's not as a crest and the other one's at a trough, which means that they'd be out of phase from each other, but they're going to be in phase. So as these guys move outward, right, what will eventually start to happen as they move outward is these guys are eventually going to overlap with each other. So as they start to overlap with each other, they're going to interfere with each other. So let's kind of talk about what's happening here. So let me also draw a trough. So these circles I'm drawing here are wave crests. So let me draw a wave trough. So this is going to be about halfway through. So this is going to be my trough, which then has the opposite orientation. So just remember, if I redraw my wave, do something like this. This guy here is the crest, which is when it's at its maximum amplitude. And then this is my trough, when this guy is at its minimum amplitude. So what's going to happen then is what? These portions here, where they interfere and they're both in their crests, then in this case, they're going to interfere with each other constructively. So at these portions here, we're then going to get constructive interference. Now, when the trough interferes, though, with the crest, what happens in these positions here is that these guys will actually give us destructive interference. And the reason for that, again, is that what? One of them would be coming in as a crest, the other one will be coming in as a trough. And as we talked about in class, if we add these two guys together, then we get zero, right? Which basically means that the destructive interference in this case is going to cause the amplitude to go to zero. And as we just spoke about, the amplitude going to zero means the intensity is going to go to zero. Now at these points here, because the amplitude is going to become twice the amplitude, so in this case, my amplitude then is going to become twice the amplitude. This means then that my intensity then is going to become equal to 4 times amplitude squared, or sorry, 2 times amplitude squared, which means that this guy is going to become same as 4 times amplitude squared, which means that my intensity then is going to become 4 times the original amount of intensity. Which means the sound is going to become much, much higher. Now, in between there, it's going to be increasing and decreasing. So basically meaning that it's going to go from zero. So in that case, you wouldn't hear anything, and it's going to slowly increase until it reaches that maximum of 4 times the original intensity. Because there, I'm not getting full destructive or full constructive interference, which is something that we're not going to mathematically talk about, but it would slowly rise up. So here, if I show you another picture of here, because my drawing, as you guys know, is only slightly fantastic. So we're going to get something that looks like this. So all that means then is if I have my two sources, right? So I have source one here and I have source two here. As these waves propagate outward, we're going to get many locations where we have constructive interference and many locations where we have destructive interference, which means as I move outward, say in some particular direction, we're going to encounter some places where we have constructive interference, some places where we have destructive interference, which means at one point we'll hear nothing. And then the sound level will increase, 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 and it becomes a maximum. And then it'll decrease, 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 decrease until we hear nothing. And then go through the whole process again, right? So what we want to know then is where are these locations of maximum and minimum interference? So basically what I want to know then is given my, two speakers in this case, where are these guys going to happen relative to say one of the speakers, or in this case, actually both of the speakers. So I'm going to have one distance here. Right? Let me call this guy, I don't know, R2. Let me call this source two. And I have source one over here. And then let's call this guy here, we use a different color. This distance here, let's call this guy R1. So how do I know where these things are actually going to occur with each other? Well, the way we do this is what's known as path length difference. So what is path length difference? So path length difference is the distance in length that a sound wave travels from each source. So basically meaning that here's source one, here's source two. Let's say here's the point of interest P. So this wave here is going to travel this distance, let's say R1. This wave here is going to travel some other distance, let's say R2. Excuse me. So now the path length difference, which we're going to call delta D, is then going to be equal to the absolute value of R2 minus R1. Now, I'm putting absolute values on there because it's always going to be a positive. So if R2 is greater than R1, of course, I can drop the absolute values. But if R1 is greater than R2, I have to put in the absolute values, or I just switch the order and I take R1 minus R2. So this guy just always has to be positive. Okay. Now, it turns out that if the path length difference between the two is a integer multiple of the wavelength. So if this guy here is proportional to some integer, let's call that guy m, times the wavelength, this is going to give me constructive interference. Now, the reason for that is if one of them has traveled, so it has only gone through a half a wavelength, where the second one has traveled so that it has gone through, so let me do it this way, a full wavelength, then in this case, by the time they interfere with each other, the two amplitudes line up with each other, which means we're going to get constructive interference, right? So this is going to be constructive. So this means then that, again, if this path length difference is then equal to the integer times the wavelength, then we're going to get constructive interference. Now, if this path length difference, delta D, is then equal to half an integer multiple of the wavelength. So in this case, we have m, which again is an integer. So m in this case is an integer, which means this guy's going to be 1, 2, actually 0. Let's do it this way. So 0, 1, 2, and etc. So the integer plus a half, make sure that it's a half. So this thing here is just going to be a half. So again, if it's a half wavelength difference, then this guy's going to lead to destructive interference. So destructive interference then means that, again, let's say that the first one traveled a half a wavelength again, but the second one is going to travel what? So in this case, a half a wavelength difference, right? So this one here is a half a wavelength. This one's a full wavelength, but in this case, it has traveled this distance here different. So again, another half a wavelength. So in this case, again, what happens then is that one of them is coming in with a crest, the other one comes in with a trough, which means the sum of the two is then equal to simply 0. So if the path length difference is any integer multiple of, again, the wavelength, then we're going to get constructive interference. So meaning if they travel the same distance, that's constructive interference. If they travel one wavelength different, that's constructive interference. If they travel two wavelength difference, then that's constructive interference. But if they travel a half integer, so a half, three halves, five halves, seven halves, and etc., then we're going to have destructive interference. So good. So let's use this and let's do an example. So let's say I have two speakers. So here's my first speaker. Here's my second speaker. And let's say these guys are separated by some distance, where that distance in this case is going to be 4 meters. Okay. Each one of them is giving out the same frequency. So the frequency in this case is equal to 171.5 hertz. And then I'm going to take some student in the room. So I don't know, let's take somebody. Who do I want to take? I've already picked on a bunch of you guys. So let's take Carl. So let's say Carl, I'm going to put here somewhere in between. So here's Carl. So there's Carl. Go. So Carl is standing here. So what we know then is that what? Carl in this case is going to be, actually, let me draw you a little bit closer over here. Match my numbers here. So here's Carl. So Carl is going to be this distance, and let's call this speaker one, this speaker two. So he's going to be a distance, let's call that R1, where R1 then is equal to what? 1.5 meters away from the left speaker. So let's say that the speed of sound in air in this case is simply equal to 343 meters per second. Now, what we want to know then is if I put Carl there, is Carl going to sue me or not? So basically meaning, am I going to have constructive interference in the point where I'm going to have too much intensity and then I'm going to break Carl's eardrums and then he's going to sue me? Or is he going to hear destructive interference at this point, meaning that I'm not going to get sued, but he might get annoyed? Right. So how would we do this problem? Well, let's first look at the path length difference. So we know the path length difference in this case is going to be the same thing as, let's call this distance here R2. Now, R2 in this case is going to be the same thing as 4 meters minus 1.5 meters, which is the same thing as what? 2.5 meters, right? So in this case, R2 is greater than R1. So I'm going to get D, or delta D, is then equal to R2 minus R1. So in this case, this is then going to be what? 2.5 meters minus then 1.5 meters, which is the same thing as simply 1 meter. So the path length difference is 1 meter. Now, so what we also know is that this is going to be something equal to some number times lambda. Now, what we want to know is this number equal to an integer, meaning that this is going to be constructive interference, or is this number equal to a half an integer, which means that this guy then is equal to destructive interference. So let's solve for that number. So this means then that number is then going to be equal then to delta D divided by the wavelength, which is the same thing as, in this case, 1 meter divided by the wavelength. Now, we don't know the wavelength, but we know the speed and we know the frequency, and we know that the velocity in air has to be equal to the wavelength times the frequency, which means our wavelength then is going to be equal to the velocity in air divided then by the frequency. Right? So plugging that in here, let's do that on the next page. So we're then going to get our path length difference divided by the wavelength, which then is equal to the number here, is then going to be equal again to 1 meter times then the frequency, because we have 1 over the wavelength. So this is going to be the frequency, which is 171.5 hertz, divided then by the wave, or the speed, where the speed is 343 meters per second. Or let me write that in a symbolic form. So this is going to be my 1 meter times my frequency divided by my speed of sound in air. So put in my numbers, what I find is this guy turns out to be exactly a half. And the reason for that is that the meters here are going to cancel. This per second is going to cancel this per second. So this ends up being a half. And of course, a half is a half integer, which means that this is actually destructive interference. So ultimately, Carl will not sue me, but he'll be annoyed and maybe not come to class tomorrow. So, so in this case, he hears nothing because it's that destructive interference. So his intensity here is at this point is zero. So he hears absolutely nothing. So the sound level in this case is zero. So let's do one that's a little more complicated. So let's do another one where let's switch to different colors, getting bored of those. Okay. So this says I have two identical speakers are located on the x-axis where the first one is at the origin and the other one is at some distance above that, which is at 2 meters. Okay. So here's my origin. So this is speaker number one. And then here's speaker number two. This is my y-axis. This is the origin, which means my x-axis is going to be in this direction. Okay? And let's say the distance between these two is some fixed distance, y, where y in this case is going to be equal to 2 meters. Okay? Now, each one of these guys has a frequency, f, where that frequency is 784 meters per second. I'm going to take a fixed velocity of sound in air, which is 344 meters per second. Okay? Now, what we want to know then is we're going to take a small microphone. So let's say here's my microphone. Okay. And then we're going to move this guy very slowly. So in this case, our velocity is very small. So V in this case is equal to very small. And the reason for that is we don't want to get a Doppler shift in this case, and we'll talk more about that later, but we're going to move this guy very small or very slowly. So we want to know then at what distances along this x-axis here will there be destructive and constructive interference. So we want to know, for example, at what locations, let's say here, here, and here, am I going to get, for example, constructive interference? And then another constructive interference. And then where am I going to get destructive interference? Okay, so what are the locations at which this is? So, so let's do this problem. So how will we do this problem? Well, what we know going back is that we want the path length difference. So let's choose some point. So let's say where the microphone is currently is the point of interest. So let's choose this as our point of P. So we know this sound wave is going to travel this distance here. So let's call this distance x, which in this case is equal to R1. This sound wave here is going to travel this distance. So this is going to be our distance R2. Okay. So in this case, we know our path length difference, delta t, is again going to be equal to R2 minus R1 because again, R2 is greater than R1. So this is going to be the same thing then, according to our picture, as R2 minus then x. Okay. Now, because we know the distance of y, we know the distance of x, we can then rewrite R2 in terms of Pythagorean's theorem, which is then going to be equal to the square roots of y squared minus x squared. So it's going to be the same thing then as the square root of y squared minus x squared minus x. Or sorry, y squared plus x squared. Is that right? Yeah, y squared plus x squared. Sorry, forgot how to do math there for a second. Okay, so this is our path length difference. Now, what we know then is, again, what? If this path length difference is equal to a half integer times the wavelength, this is going to be destructive interference. And we know if this guy is going to be equal to an integer multiple of the wavelength, this is going to give us constructive interference. Now, I don't know about you, but I'm too lazy to do this separately, so I'm going to define both of these two together as simply n times lambda, where n can be either an integer or a half integer. So that means that anytime I use n is equal to an integer, then in that case, I'm going to get constructive interference. But if I use n as a half integer, I'm going to get destructive interference. So basically, all this means then is I want to take the square root of x squared plus y squared minus x and set that equal to n times lambda. So in this case, since we want to know the locations of x, we're simply going to solve this guy for these x's. Right? And then after we're done, we're going to choose all of our different n values, starting off with 0 and then a half and then 1 and then et cetera, and then keep track of which one is constructive versus destructive. So we're just going to do both of them simultaneously because we can. So good. So let's start off by solving this guy. So first things first is we notice that we have a square root on the left-hand side. So the most natural thing to get rid of a square root, of course, is squaring. Now, if I square in this form here, The problem with that is we're going to get a cross term, which is still a square root, right? So we don't want to do that. So first thing we're going to do is we're going to bring this x to the other side. So let's do that. So let's add the x term. So we're going to get x squared plus y squared square rooted then is going to be equal to n times lambda plus x, right, based off of our previous example. So now all we're going to do then is square both sides. So my left-hand side is going to become x squared plus y squared is then equal to, so let's multiply out the second term. So I get the first term squared. So I'm going to n squared lambda squared plus the second term squared, which is x squared, plus 2 times the cross term. So n times lambda times x. Now, when I first look at this, I'm going to assume that, oh, great, I have to solve a quadratic, bleh, right? But notice that I don't have to because I have an x squared here and I have an x squared here. So those two x squareds are going to cancel, which means I actually have a linear to solve. Yay, not a quadratic. So let's do that. So I'm going to get y squared then is equal to n squared lambda squared plus 2 times n times lambda times x. Now, again, what I want is simply x. So let's move this term to the other side. So I'm going to get a lambda squared minus n, or sorry, y squared minus n squared lambda squared is then equal to 2n lambda x. And now let's divide anything that's not an x. So finally, we get x then is equal to y squared minus n squared lambda squared divided by 2n lambda. Where lambda in this case, because again, we don't know the wavelength, but we know the speed of sound in air and the frequency. So this is going to be V air divided by the frequency, which we can do later. I'm not worried about that right now. So good. So this is our general expression that we have to solve. Now, again, for constructive interference, all we're going to do is set n equal to integers, starting off with 0. So we're going to get 0, 1, 2, and then etc. Right? And we want to do this until we get a negative number. And the reason we want to do that is going back to the problem. What we want to know is only the locations on the positive x-axis. So in this case, once our x value becomes negative, that means we're on the negative side. So in that case, we're going to ignore it. Okay. And then we're going to do the same thing. So for destructive interference, we're then going to set n then is equal to a half integer, which means that this guy's going to be equal to what? 1/2, 3/2, 5/2, and etc. until eventually, again, our x becomes negative. So let's go ahead and do this. Let's start this off for some particular values here. So I'm going to arbitrarily start with constructive interference. So let's look at constructive interference. So first one at n is equal to 0. So for n is equal to 0, let's see what we get here. So we get x0 is then equal to y squared minus 0 squared, of course, times the wavelength, but I'm not caring about that, divided by 0, right? So this 0 doesn't matter. So I get anything divided by 0 is then equal to infinity. Right? So the first one is actually infinite. So let's think about what that means. So what this means is that, again, our path length difference is equal to 0 times the wavelength, which is simply equal to 0. So each one of these two waves has to travel the same distance. Now let's go back to our picture. So all that means then is that this one has to travel the same distance that this one travels. Now, the only way for that to be true is what? So even if I draw this one here, we can see that what? The distance R2 is always going to be greater than R1. Now, the only way that this makes logical sense is if we go all the way out to infinity, because what? In that case, each one of these guys will travel a parallel line. And if I go infinite distance away, it appears as the distance between each one of these two guys shrinks to 0. So in this case, the only way to get parallel lines is if we go all the way out to infinity. So this means, again, going back to my picture, excuse me, the first place I find a constructive interference is at x0 all the way at infinity. So I have to go all the way to spatial infinity to get my first one. Now, next one, of course, is going to occur at n is equal to 1. In this case, of course, this term is no longer 0. This term is no longer infinity. So if I plug in my numbers, what I get in this case then is that x1 and ends up being 4.34 meters. So I'm going to go all the way out to infinity and then all the way into 4.34 meters away from the source 1 to find my next one. N equals 2, then we're going to get x2, which is then equal to 1.84 meters. So I have to now go another almost 3 meters. N is equal to 3. We're going to get x3 then is equal to 0.86 meters. And then finally, n is equal to 4. We get x4 is equal to 0.26 meters. So again, simply plugging in all the expressions for these guys here. Now, so notice each one gets closer and closer and closer and closer to the speaker itself, S1 here. And then if I go to n is equal to 5, I get simply a negative number, which again, all we want is the positive x-axis. So let's do the same thing now for constructive. Actually, we won't because I'm out of time here. So in this case, we'll finish this off tomorrow in class. And yeah, we'll call it a day. So in that case, then we'll keep moving on from there. All right, I'll see everybody tomorrow. And yeah, have a good day till then. Bye.